Assalamu alaikum, students and friends. This video tutorial is a prelude of a lecture series on periodicity of elements, focusing on the features of the modern periodic table of elements that will allow you to easily compare the properties of one element to another. So, stick around, watch and learn. The question is, for each of the following elements, give the electron configuration, period, group, and valence electrons. Number 1, aluminum with 13 as an atomic number. Number 2, sulfur with atomic number 16 and bromine atomic number 35. A periodic table is an arrangement of elements in which the elements are separated into groups based on a set of repeating properties. Each horizontal row is called a period. We have period 1, which contains only the hydrogen and the noble gas helium elements. Period 2, starting with lithium, and far right is neon. Period 3, starting with sodium up to the noble gas argon. Period 4, with potassium as the first element and the noble gas krypton as the last element. Period 5 begins with rubidium and farthest right is another gas or noble gas xenon. Period 6, starting with cesium and ends with the noble gas radon. All right. Period 6 also includes the what we call lanthanide series. All right. They are supposed to be inserted after the element barium. All right. And lastly, we have period 7, beginning with francium. All right. And period 7 also includes the actinide series, supposed to be inserted after the element radium. All right. The farthest element within period 7 is the synthetic element, the bermorium, with symbol capital L, small v, and with an atomic number 116. Each vertical column is called a group or a family. Elements in a group have similar chemical and physical properties identified with a number and either the letter A or B. Groups 1A to 7A are known as representative elements. And the group B elements are called the transition metals. In other versions of the periodic table, all the groups are simply named group 1, group 2, group 3, and so on until group 18. All right? So, group 3A, for example, is named simply as group 13. The halogen group, right? Um, Normally, we call it group 7A, all right? But in some versions of the periodic table, it is simply named as group 17. In the old version of the modern periodic table, pioneered by Dmitry Mendeleev, the elements were arranged according to increasing atomic mass. But an English physicist named Henry G. Moseley observed that frequencies of X-rays emitted from elements could be correlated better with atomic numbers. All right? He found out that the properties of the elements are periodic functions of their atomic number. And uh, unlike in Mendeleev's original version, in Moseley's version, all right, the elements in the periodic table are now arranged in the order of their increasing atomic number. A group is often called a family because of the similarity of the elements within it. A family is usually given a name, and these are the families and their special names. We have group 1A, also known as the alkali metals. Group 2A are called alkaline earth metals. Group 3A are the boron family. Group 4A are called carbon family. Group 5A are the nitrogen family. Group 6A are called the oxygen family. Group 7A are called the halogen family. And group 8A, all right, are the noble gases. Group 8A, more commonly called the noble gases, all right, uh, such as helium, neon, argon, krypton, xenon, and radon, these noble gases have very stable configurations, meaning they have very little tendency to react with other elements under proper ordinary conditions. A very important feature of the modern periodic table is the way the groups are classified in terms of the way their sub-energy levels and orbitals S, P, D, and F are filled with electrons. For instance, in groups 1A and 2A, all right, their s orbitals are filled or are being filled by electrons, and hence they're called the s block elements. In groups 3A up to 7A, okay, the p orbitals are being filled with electrons, hence they are called the p block elements. For group B elements known as the transition metals, uh, the d orbitals are being filled. All right, so they are called the d block elements. The lanthanide or rare earth series and the actinide series, all right, the f orbitals are being filled, so they are known as the f block elements. In writing the electron configuration of an element, the given Upball principle mnemonic device may be used as a guide. Based on Upball principle, all right, electrons will fill the lower energy orbitals first. All right. So, as shown in this diagram, okay, in writing the electron configuration of a given element, all right, and its atomic number, you just follow the direction of the arrows, all right, beginning with, of course, 1s, and then 2s, followed by 2p, 3s, then 3p, 4s, and then 3d, 4p, 5s, and so on, all right, depending on what the atomic number of the element is. You will notice that after 3d, all right, or after 4s, we have 3d, all right. So it's one of the what we call overlapping of the orbitals. Okay, there are some overlapping, all right, of the different orbitals, but this is according to Upball principle. These orbitals or sub-energy levels are arranged, okay, in terms of the energy from lowest energy to the highest energy. All right. Likewise, the maximum number of electrons that can stay in each sub-energy level, all right, is given here. For s orbital, okay, there can only be two maximum electrons. For the p orbitals, there can be six maximum number of electrons. For the d orbital, the maximum number of electrons is 10, and for the f orbital, the maximum number of electrons is 14. All right? So this is actually based on Pauli's exclusion principle, which requires that only a maximum of 2 electrons can occupy a given orbital. All right? So let's go back to our SPDF sublevels. All right? There is only one s orbital. So it can accommodate only one or two electrons. Okay? There are three p orbitals, sometimes denoted as px, py, and pz. So multiply that by 2. That's why a maximum of 6 electrons, okay, can be accommodated in the p orbitals. For the d orbitals, there are 5 different d orbitals, commonly uh, denoted as dx, dy, dz, dxy, and dxz. All right? So 5 times 2, we have 10. 10 maximum electrons can be accommodated in the d orbitals. Now, for f orbitals, there are 7 different f orbitals. All right? We can differentiate the 7 f orbitals by using the notation uh, fx, fy, all right, fz, fxy, fxz, and so on, all right, until you have the 7 different notations for the f orbital. So 7 times 2, that gives us 14 as the maximum number of electrons that can occupy the f orbitals. All right? Now, another important rule is the Hans rule of maximum multiplicity, or simply the Hans rule. All right? Which states that in the orbitals of the same subshell, meaning for orbitals uh, such as p orbitals, all right, where there are 3 px, py, and pz, all right, or for d orbitals, since there are 5 different d orbitals, all right, according to Hans' rule, um, electrons are filled singly first before pairing starts. All right. So, to illustrate these two rules, all right, supposing you are to write the electron configuration of the element oxygen, whose atomic number is 8, all right? And imagine that these boxes represent uh, the different orbitals. We have the 1s orbital, we have the 2s orbital, right? And the 3 uh, p orbitals, or 2p orbitals. So there are 5 orbitals. So um, we're going to start with, of course, the first electron occupying the lowest, or the orbital with the lowest energy, which is the 1s orbital. And assuming that each electron is represented by an arrow, all right, either spin up or spin down. So the first electron, of course, will fill up the 1s orbital. And the second orbital, or the second electron, will still go to the 1s sublevel. All right. So the first, what we call energy level, is already complete with 2 electrons, 1s, 2. The third electron, of course, will have to fill the next higher energy level, which is the 2s, all right, orbital. So we have the third spin up electron. Now, the fourth electron we'll still go to the 2s orbital, right? And we say that these orbitals such as 1s and 2s are already complete with 2 electrons. In terms of stability, we say that these electrons are already stable in their respective 1s and 2s orbitals. All right? So we already have 4 electrons uh, having been accommodated. So let's proceed to the fifth electron. All right? The next orbital with a higher energy, of course, belongs to the 2p orbitals. Since there are 3 of them, all right, whichever has the least amount of energy, that is where the fifth electron will go. All right, so speed up, that's the fifth electron. Now, at this point, where do you think will the sixth electron go? In which p orbital will it fill? All right, the answer is it will go to the next p orbital. All right, that is according to Hahn rule. All right, so the sixth electron doesn't want to immediately pair with the fifth electron. All right, but instead it prefers to go to the next empty p orbital. All right, now we have 2 more electrons. The seventh electron, just like the sixth electron, we also have to choose, okay, the last p orbital being an empty orbital. All right, so it looks like uh, the way these electrons fill the orbitals, it's like the behavior of passengers, okay, riding a bus. All right, people would tend to first occupy the empty seats in the bus. All right, so that's just an analogy. Now we go to the last electron. All right, the last or eighth electron has no other choice but to pair up with uh, the electron located in the orbital with the least energy. All right, and that is all right in the first p or 2p orbital. So that completes the 8 electrons already accommodated in the uh, what we call 1s, 2s, and 2p orbitals. And of course, the final configuration for oxygen, we say, is 1s2, 2s2, and 2p4. Moving on now to our answers to the questions. All right. Number one, question number one, you are to give the electron configuration, the period, the group, and the valence electrons of the element aluminum with atomic number 13. So, its configuration following the Opbau mnemonic device, all right, we have 1s2, 2s2, 2p6, 3s2, and 3p1. All right, so 2, 4, plus 6, 10, plus 3, 13. All right? Always check the number of electrons that you put in this configuration. There should be 13. All right? We can also use what we call the noble gas notation, such as, in this case, bracket neon. All right? Bracket neon, whose atomic number is 10, represents the inner electrons of aluminum. All right? So instead of uh, giving the 1s2, 2s2, 2p6, all right, configuration, we just use the bracket neon, all right, a shortcut way, and only add to the bracket neon what we call the outermost configuration, all right, and that is 3s2, 3p1, all right, check, 10 plus 2 plus 1, you still have the 13 electrons being represented correctly, all right. Now, based on this electron configuration, we can already tell what the period of this element is. All right? We say aluminum 13 belongs to period 3. That is because uh, its outermost energy level occupied by electrons is the main energy level, n equals 3. All right? And for the group number, all right, we first count what is the valence electrons of aluminum as shown in this configuration. All right, so there it is. The valence electrons is 3. What does that mean? All right, by definition, valence electrons refers to the number of electrons in the outermost energy level. All right, so the outermost energy level, of course, is 3. The orbitals in the outermost configuration are 3s2 and 3p1. All right? So the number of electrons, 1 plus 2, represents the valence electrons. All right? And earlier we said that the valence electrons can also tell the group number of the element. In this case, aluminum belongs to group 3A. All right? So whatever is the valence number, that corresponds to the group number, which is group 3. All right? Or group 3A. How do we know that it is a representative element? Okay. Why did we describe it as group 3A? It is because in the configuration, you will notice that the p orbitals are being filled, all right, with electrons. In this case, 3p1 is not yet fully filled. All right, that is still being filled. Hence, earlier we said that if the p orbitals is being filled with electrons, that element is considered or belongs to what we call the p block elements. Right? So aluminum 13 or aluminum with atomic number 13, all right, to summarize the answers, belongs to period 3, group 3A, with a valence electrons of 3, and whose electron configuration is shown as bracket neon 3s2, 3p1. Alright, for question number 2, we are given the element sulfur. Its electron configuration, since the atomic number is 16, alright, will be 1s2, 2s2, 2p6, 3s2, and 3p4. Or using the shortcut method, that will be bracket neon 3s2, 3p4. Alright? So its period number is period 3 because the outermost energy level is n equals 3. And its valence electrons, alright, of course, is 2 plus 4, so that is 6. And we say that sulfur belongs to group or family 6A, alright? Since it is the p block or the p orbitals that is being filled with electrons, therefore sulfur belongs to the group or the p block group of elements. All right. So, as a summary, sulfur belongs to period 3, group 6A, with valence electron 6, and with an electron configuration bracket neon 3s2, 3p4. And lastly, question number 3, we are given bromine with atomic number 35. All right. So its configuration is quite long. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p5. All right. So you may check using the Opbau mnemonic device. Notice that the 3d10, all right, comes before the 4p5. This can also be written in a shortcut manner using the noble gas notation. All right. The inner electrons of bromine, 18 electrons that is, can be represented by the noble gas argon. All right. So we just include here the outermost configuration, which is 4s2, 3d10, 4p5. And bromine therefore belongs to period 4 because the fourth energy level is the outermost, all right, energy level occupied by electrons. And its valence electron, of course, is 2 plus 5, that is 7, all right? So we say that the group number of this element is group 7A, that is the halogen group. Since it is the p orbitals that is being filled, notice it's not yet complete, 4p5, all right? Hence, bromine belongs to the p block of elements, all right? In fact, it belongs to the halogen group of elements. So summarizing our answers, bromine has this configuration, bracket argon 4s2, 3d10, 4p5, belonging to period 4, group 7a, and with a valence electron equal to 7. Right? So that ends my presentation. Till the next episode, mabuhay, inshallah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.